I am so glad you're here for another episode of Mechanism Monday, where every Monday we write out the electron-pushing arrow mechanisms for different organic reactions. In last week's video, I asked if you could solve the mechanism for this organic transformation, so if you haven't had a chance, pause the video now and try it independently. And make sure you stick around to the end because I'll give you another mechanism to solve for next week's video. This summer, I'm teaching organic chemistry too, so to be honest with you, this reaction is meant to help my students taking my class this summer. But I thought it also might be a good refresher for you, especially if you struggle with things like decarboxylation reactions. And importantly, this reaction relies on a lot of really fundamental chemistry that you should probably brush up on anyway. The first step in this reaction is going to be to deprotonate one of the alpha carbon hydrogens located at this alpha carbon position. Because remember, sodium methoxide is a really strong base, so we can think of this as just OET minus, and it can come in and deprotonate one of those hydrogen positions, giving us an enolate at this position. So I'll just redraw this as the product where we've placed the negative charge on that carbon. So now we have a lone pair of electrons, which is going to make this negatively charged. And this is one of the resonance structures that are possible for this structure. So I'll draw in the rest of our molecule, and what can happen next is known as an alpha alkylation. So we have generated a brand new nucleophile at this position because of the incredibly acidic protons here. And following that deprotonation, we've generated this nucleophile which can come in and attack an alkyl halide. And this reaction is known as an alpha alkylation. So it can come in and attack this position, kick off the iodide as a good leaving group, just like in an SN2 type reaction. So from here, what we've done is we've placed a new alkyl chain at that carbon position. And this is a very common reaction type in organic chemistry too. And again, it's called alpha alkylation. And then remember, the next step is to add an acid and heat. And this is just a common way to do the acid-catalyzed formation of carboxylic acids from esters. This is a very common reaction type, and I actually have videos here that you can check out to review that process. So what we've now done is generated a new dicarboxylic acid at this position, and then remember, we still have generated that brand new alkyl chain at this alpha carbon. So what happens next to get us to our final product is known as a decarboxylation. And this is the part that my students in the past have typically struggled with. So I'm making this video to hopefully help them out. So I've drawn our dicarboxylic acid in this orientation, but in fact, what I'm going to do is redraw this. So all I'm doing is rotating around this carbon position to place our carboxylic acid instead in this orientation. Where again, all I've done is rotated around that bond so you can see the OH group is here, and I've purposefully drawn in this OH group of our carboxylic acid so you can see what happens next. Because from here, what will happen is that this neighboring carboxylic acid has lone pairs on the oxygen, and they will come and abstract that proton, which will kick down these pi electrons to make a brand new carbon to oxygen double bond here. And rather than moving these pi electrons up to this oxygen, what will actually happen is this will actually liberate CO2 as a gas and bring down the electrons down to this position. So that will then kick up these pi electrons. And again, we lose CO2 as a part of this process, and all you need is an open reaction flask, and CO2 can leave, which would be driving force for this reaction following Le Chatelier's principle. So then notice what we've done here is we've created a brand new species where now we have these two OH groups, we've lost CO2, and all that remains is this carbon chain. So from here, all that needs to happen, since we have this brand new alkene located at this carbon with these two oxygens, is just a keto-enol tautomerisation. And following that keto-enol tautomerisation, you actually generate your final product. So again, we started by taking this diester, turning it into a single carboxylic acid, and just extended our carbon chain. First, by deprotonating the alpha carbon hydrogen using sodium methoxide, doing an alpha alkylation reaction, which is an SN2 type reaction between our enolate species and an alkyl halide, and then subsequently adding acid to turn those esters into carboxylic acids. And then by introducing heat and having plenty of acid around, we can do this final step, which is known as a decarboxylation. And then subsequently, the keto-enol tautomerisation gets us to our final product. If you enjoyed this week's mechanism, give it a thumbs up down below. And for next week, I'd love to see if you could figure out the electron-pushing arrow mechanism for this organic reaction. Drop your thoughts as a comment down below, and make sure that you subscribe to the channel so that you never miss out. I'll see you next week.